I've got a resistor, I've got a capacitor. With these two things, I can build a low pass and a high pass filter, and so can you. Let's investigate how these two things function as a filter. So, if I take, I'm going to start by taking my resistor and putting it in series with a capacitor. So I have this circuit here. Now, before we go any further, I will say that in our course, Signals and Systems, you don't need to know circuit analysis. I will give you all of the circuit analysis that you need on any homework or exam problem. Now, in our RC circuit, let's say that the voltage across the series combination is the input. Call that X of t. So this could be coming from an antenna, or maybe another electronic or electric circuit, or maybe an MP3 player or something like that. And then we'll take the voltage across the capacitor as our output. So this would be sent to maybe an amplifier or a speaker, or maybe another analog circuit or electronic circuit or something like that. Now, let's recall, and again, you don't need to know this, but the impedance of a capacitor is 1 over j omega c, where omega is the frequency of the sinusoid as it's always been. C is the capacitance, and j is the square root of -1. And the impedance of a resistor is just R, where R is the resistance. So R and C are constants in our circuit. Now, from voltage division, and you don't need to know voltage division. So voltage division tells us that the output is related to the input by 1 over j omega c over 1 over j omega c plus R. And actually, it turns out that that's the frequency response. So not only do you not need to know voltage division, you do not need to know why this is the frequency response. You can just take my word for that. And I can clean this up if I multiply the numerator by j omega c and the denominator by j omega c, then I get 1 over 1 plus j omega rc. Right? And that is the frequency response of this RC circuit. It's very simple. As we've shown before, we might need the magnitude of the frequency response. That's called the magnitude response. And we might need the phase of the frequency response, called the phase response. So let's start with the magnitude of this complex number. The magnitude of the numerator is simply 1. There's nothing fancy going on there. And in the denominator, I have a real part, 1, and an imaginary part, omega rc. So we can quickly find the magnitude of the denominator by Pythagorean theorem, 1 squared plus omega rc squared. That is the square of the real part and the square of the imaginary part. So of course this is 1 over the square root of 1 plus omega squared r squared c squared. That's the magnitude response. And just to be complete, the phase response. So if I take the phase of this complex number, the phase of 1 is 0, minus the phase of the denominator is the inverse tangent of the imaginary part over the real part. So this is just omega rc. And of course we don't need to write the 0, so I'll just write it like this. Now let's recall from the previous video, an ideal low-pass filter has this magnitude response. I'll write magnitude of ideal that it's got some omega c, some cutoff frequency, and for frequencies in magnitude less than omega c, they pass through the low-pass filter perfectly with a gain of 1. And then frequencies larger in magnitude than omega c are attenuated perfectly by a factor of 0. So they go away completely. And the ideal phase response of a low-pass filter, let me get black there, okay. The ideal phase response looks like this. It's just 0 There's no phase distortion for any frequencies. Now let's see what we have. And actually, before that, I said that these are impossible to build. We just approximate them. So let's see what we've got here. Let's plot the magnitude response of our RC circuit. So here's the magnitude response of what we're dealing with. Now, so we need to make a plot of this. So you're going to choose a value of R and C. You have a specific resistor and you have a specific capacitor. So you can pick values of R and C and then plot this versus omega. And you'll notice that when omega is 0, then I have the denominator is the smallest it can be, and so the fraction is the largest it can be, which is 1. So I'll put that point right there. When omega is 0, the frequency or the magnitude response is 1. And then as omega goes to infinity, this is 1 divided by infinity, which is 0, so it's going to go like this. And when omega is minus infinity, because of the square, that becomes positive infinity, and so I have the same thing over here. Okay, that's an even function. And the phase response, I'll draw that just to be complete. If you were to, again, pick values of R and C and then plot this versus omega, what you would see is something that looks like this, where this is 90 degrees, this is negative 90 degrees, and again, this is the phase response. Okay, now there's a very special value in electronics, and that's when the gain is 0.707. So it turns out that when you put in omega is equal to 1 over RC, you get 0.707 there. And because this is an even function, when you put negative 1 over RC, you also get 0.707 there. Why 0.707 is important is outside of the scope of the course. And when you put in 1 over RC here, you get negative 45 degrees. And this is an odd function, so when you put negative 1 over RC here, you get 45 degrees. Now, 0.707 actually defines the bandwidth of the circuit. So we would call this frequency the bandwidth, or to relate it back to the low pass filter, that's this cutoff frequency. That's omega C. You see, because even though this is not exactly like this over here, it's approximately. Frequencies around or less than 1 over RC, so frequencies around here, are approximately scaled by the value 1, like it is here, right? And then for frequencies larger than 1 over RC, they're attenuated by something very small, close to 0, like it is here. So this is an approximate low-pass filter, you see? And the phase is kept small. The phase is less than 45 degrees for frequencies within the pass band, right? And then they're much larger. They're larger than 45 degrees in magnitude when they're outside of the pass band. So that is why we can use the RC circuit as a low-pass filter. Pretty neat, right? Okay, now you should have a handle there of why the RC circuit is a low-pass filter. And now I'm going to go a little bit further and try to draw in concepts from prerequisite course, circuit analysis. We said this was the frequency response of the RC circuit. It turns out that the impulse response is this. This thing here. We will show that later on in the course. But these two things make up a pair. They're almost like a pair, where if a circuit has this or a system has this frequency response, it can be shown that it has this impulse response and vice versa. So these two things are a pair. Okay, now let me draw that RC circuit again. In circuit analysis, you had a problem where, or you would have seen a similar problem to this, where you had 1 volt and you connected it to your RC circuit and you switched in that 1 volt at time t equals 0, right? And then you were asked to find the capacitor voltage. And what you found, this is time and this is y of t, what you found is it's 0 until you switch it in, of course, because without any voltage, you know, you have a 0 voltage across the capacitor. Then when you switch it in, the capacitor starts to charge, and it charges up to 1 volt, right? But it never quite gets there. And you actually found the equation of this line, this curve, and the equation for that was 1 minus e to the negative t over RC. So it's 0, and then it becomes 1 minus e to the negative t over RC. All right, and the way you did this was you found the steady state response of the capacitor at infinity and at 0. You found the time constant, and then you found this equation by solving a differential equation. And then you applied Kirchhoff's voltage law around the loop to get that differential equation, and then you solved it. So we're not going to use circuit analysis in our course, but we're going to see if we can get this using techniques that we've covered in our course, using the impulse response. Okay, so this here is the voltage across the combination, and we said that it's 0 until t equals 0, and then the 1 volt gets switched in, so the voltage looks like this. Well, what's that equation? Well, that's a unit step. So what we're saying in our class is we have this circuit, and it's linear because our resistors and capacitors are linear, and it's time invariant because resistances don't change over time. Capacitances don't change over time. So this circuit is linear time invariant. And we're putting in a unit step, right? The voltage was 0 and then became 1, and we want to know what do we get out. And we have the linear time invariance impulse response. It's this thing, which you can get from the frequency response. So how do we get y of t? Well, we convolve the unit step with the impulse response. So I'm going to do this rather quickly, and I'm going to assume that you know convolution. I'm going to flip the unit step and plot it versus tau. So this is u of minus tau. And then right below that, I'm going to draw the impulse response versus tau. So the impulse response is 0 because of the unit step, and then it decays like this. And this is 1 over RC e to the negative tau over RC. Okay? Now, for the convolution, notice that y of t is equal to 0 for t less than 0. And that's because that if I shift this graph, which I flipped already, if I shift it to the left at all, there's no non-zero overlap. So if shifting it to the left is t less than 0. No non-zero overlap means y of t is equal to 0. Now for t greater than 0, I shift this thing to the right, and my non-zero overlap then is from 0 to t, right? 0 to however much I shifted it by. And I can drop the unit steps since this is the non-zero part, and in the non-zero part, unit steps are equal to 1. So then I'm just left with 1 over RC e to the negative tau RC d tau. Okay, so I need to do that integration. 1 over RC is a constant. E to the negative t over RC. When I integrate that, I get a constant negative RC e to the negative tau over RC, right, from 0 to t. So then RC's cancel. This is negative e to the negative tau over RC, evaluated from 0 to t. And I plug in t, and I get negative e to the negative t over RC. And I plug in 0, and I get e to the 0 is 1. So I get a negative negative 1 plus 1. So this is 1 minus e to the negative t over RC. And wouldn't you know, that's exactly what you got in circuit analysis here, right? Except we did it in a completely different way. And remember that this was for t greater than 0. For t less than 0, this applied. That's this part, right? T equals 0, or y equals 0 here. And so we can put those two pieces together using the unit step. And we say for all time, y of t is equal to 1 minus e to the negative t over RC times the unit step, right? Because the unit step is 0 here, and then it's 1 here. So then we would have 1 times this over here. And so that's it. That's amazing, right? I mean, we got that two completely different ways. So now, I do have a little bit more that I want to say about this RC circuit. And in the next video, we're going to code it up in software. So, you know, if you actually had a resistor and you actually had a capacitor, you can make an analog circuit, and this would be a continuous time system like we have here. But we can I don't want to say simulate, but we can maybe discretize, meaning we convert to discrete. We can discretize this system into a computer program that does the same thing, i.e. a low-pass filter, but for discrete time. So that's the next video, and I'll see you then.